Okay, we are on page 18. So we're on page 18 and we're going to be doing the Lewis structure for CO. Do you guys want to try that one on your own? Make sure you've got some paper. I did something wrong. I'm an idiot. There we go. That's better. So if you want to, you can check and see, did you get the same initial structure as I did? Did you get the same electrons in step 4 and step 1? Did you get that you have 2 extra pairs too many? If we have too many pairs, what do we have to do? we have to erase how many 2 lone pairs? How did I know to erase 2 lone pairs? Because we have 2 pairs too many. And usually it will be from which atom? Central atom. Now, this is a diatomic molecule. It does not have a central atom, so it doesn't matter where you erase them from. You can erase the 2 pairs from one of them. You can erase 2 pairs from the other. You can erase 1 pair from both. You'll end up with the same structure regardless. Okay? I'm going to erase 1 from each, just because I like symmetry. What's step 5B? Turn how many? 2 lone pairs into how many? 2 bonding pairs. Okay, now what if I did this? Let's see. What if I did this? Is that a happy structure? No, why not? Carbon has only 6 and oxygen has 10. Okay, so this is a no, definitely not. We have to turn the lone pairs into the bonding pairs until all atoms have 8. So instead of doing that, we say oxygen doesn't have enough and carbon doesn't have enough. That means carbon needs to share with oxygen and oxygen needs to share with carbon. So we're going to take a lone pair here and a lone pair here, and we're going to move them into the center there. And now we should just double check to make sure we have the right number of electrons. We have 3 lines, so that's 6 electrons. We have 2 lone pairs, so that's 4 electrons, which means we have 10 electrons. Is that what we had in step 1? Yes. What else should we check? And I'm going to go through the whole list here, even though we don't have certain things. What else should we be checking for? We should check that everybody has 8 electrons. And that is a correct statement. If we have hydrogen and fluorine, what do we check for? No double bonds. Well, we don't have any, so that's obviously a check mark. We should check for no singleton electrons. Nope, everybody's got a pair. And I think that's it. Oh, you should also check for B ball in case you missed it the first time, right? If you went through and you're like, oops, I gave aluminum 8 electrons, okay? And we don't have any of those, so obviously that's correct. Okay? And that's it for that. And now we're going to go on to polyatomic ions, and they also have some multiple bonds. Really, there's only 2 things that are different. Number 1 is we have to do something fancy when we're counting the valence electrons, because the charge changes the number of valence electrons. So this is on page 26. Let's make sure I'm getting sound. I'm getting sound. Yay. Okay. So if you have a positive charge, you're going to subtract electrons. What do you get if you subtract -1? You get +1. So to make an ion positive, you need to take away an electron. Does that make sense? If it was 2 positive, you would take away 2 electrons. Now, if the charge of the thingamadooey, the polyatomic ion, is negative, we need to add electrons, right? So if we had, let's say we had X2 minus, well, we would have to be adding -2. So that would be adding 2 electrons. Okay, so I'm going to do NH4 over on the side. Here's NH4. So step number 1, count the valence electrons. So we have nitrogen, which has 5 valence electrons. We have 4 hydrogens, each of which has 1 valence electron. And now we need to take care of this charge. What do we do for that charge? It's positive. We -1 electron. Or you can just subtract 1. You can put plus -1. No, hang on. What am I doing? It's just -1. It's just -1. What is wrong with me? I'm so sorry. My brain, it's been a little fried. Okay. If it's positive, you subtract 1. If it's +2, you subtract 2. Okay, got it. And then it's just like it was. The only thing is you have to remember when you get to the end, you put square brackets around it and a charge on the outside. So do you guys want to try this one on your own? Okay, go for it. So weird. Yes? Fairly straightforward? Okay. Do you guys want to try the next one? SO42 minus? Oh, and by the way, in terms of how much work you need to show, the only things I would say are necessary are showing your valence electrons and showing a correct final structure. How you get to that correct final structure is up to you. You can show work, you cannot show work. Doesn't matter. If you're getting it wrong, then go back to showing the work. Yes? Oh, because I cannot count at all. Thank you. 32. 32. What did I do? I don't know. Oh, I think I said 4 plus 6 is 10 plus, yeah, okay. Like, how did I do that even? Are we good? Okay. It just means you have 2 more electrons to work with in the structure. Yeah. Whoa.
What if we put the egg more towards the floor? I can't add.
It's okay. I got 18 when I should have got 32. So we all have our issues, right?
No, but I got 104.
Whoa, how'd you get 100? That's exciting. Okay. Okay, are we good with sulfate?
Yes.
Okay, let's try a more challenging one. HCO2. Why don't you guys give that one a go on your own? We'll check in when we get to the skeleton structure because it needs a bit of thinking. Is it 18 this time? Did I do it right?
Yes.
Okay. What do you guys think of my 2 possible skeleton structures? Which one do you like better, the first one or the second one? First one. I agree with you, but why? They're more further apart. Well, there's a few reasons, okay? Our chemical formula says HCO2 minus. What that tells me is that probably the H is attached to the C, okay, because it's touching the C. So that's a good guess, all right? This structure is also more symmetrical. And it also has carbon more central. Okay, so there we go. So check your skeleton structure, see if it's the same as mine with the lone pairs on it. Check to see if your electron counts are the same as mine. And what do we have to do if there's one pair too many? We erase what? One pair, lone pair, from the central atom. And step 5 never just has a part A, it always has a part B. And in this case, we're going to turn how many pairs? One lone pair into a bonding pair. Does it matter which one I choose? No, they're all the same, right? It all ends up in the same result. So I'm going to pick this one. And then remember, what is step 6? Is it an ion? Yes, it is. What do we need to add? Brackets. And the charge. And while we're at it, why this is all we would really need to know for this. We're going to talk more about things next day, but let's go check through our list on our orange sheet, because after step 6, it asks, are there resonance structures? And in this case, there are, and I'm going to show you really quickly what they look like, okay? So if there are resonance structures, you have to draw them. So we're going to just get a preview of what a resonance structure is. Have you heard the word resonance or resonant? If a bell rings, it goes bong, 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 bong. You know that? Okay. It means going back and forth. Resonating, going back and forth. Okay? So, this can actually go back and forth between this structure. Anyone want to guess what the other structure is going to look like? It's going to look like the first one, except what? I'm going to move the double bond. Instead of being on the left, I'm going to put it on the right, which means how many lone pairs on the right-hand oxygen now? 2. And now what kind of bond do I have on the left? Single bond. How many lone pairs on that oxygen? 3. 1, 2, 3. These guys together are called resonance structures. And we always show double-headed arrows between them. And the reason for the double-headed arrow is that first it's this one, then it's that one, then it's this one, then it's that one. Boom, 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 boom. Yes? First this, then that, then this, then that. Now, if you're wondering how this happens, it's not a flipping of the molecule. Okay, it's not just that the molecule is going whoop. Yeah, it's not like here I am, now here I am. Not like that. Okay? We're actually moving electrons. So let's see what that would look like. How do we get from structure A to structure B? Well, in order to get a double bond on the right-hand side, I'm going to need to take a pair of a lone pair, and I'm going to need to move it here. That's going to give me that double bond, yeah? Sadly, though, if I only do that, how many bonds will carbon have? It'll have 5. That's not allowed, right? So we're going to have to take this bond and do what with it? We're going to have to take it away, but not just take it away because we can't change the number of electrons. It's going to turn into a lone pair. Yeah? And then you'll have it go backwards. You'll have this pair go in here and this one kick out here. Yeah? You would not have to show this process, but that's how it goes. You get one bond comes in and forms and the other kicks out a lone pair. This lone pair comes in and forms a bond and the other one kicks out there. So it's like I'm not sure the sound effects made it any better, but there we are. So if you are asked to draw Lewis structures, this is the best representation we can get with a Lewis structure. It shows how many electrons we have. It shows that that double bond is spending half its time on the left and half its time on the right. But if we go out of the realm of a Lewis structure and we sort of go into a different kind of a structure that's almost, it's a Lewis-ish structure, a Lewis-ish structure. In reality, what we have here, we don't have one bond that's double bond half the time and single bond half the time. What we actually have is yes. Right? Oh, yeah. And this is no longer a single bond or a double bond. It is a 1.5 bond. And this one over here is no longer a single bond or a double bond. It is a 1.5 bond. The 1 comes from the single bond that doesn't move, yes? And the half comes from the fact that the double bond spends half its time over here and half its time over there. Half, half. Except that in reality, it doesn't go back and forth and back and forth. Those 2 electrons are smeared over both of those bonds. They are delocalized. They are not locked in one place. There is an orbital that kind of goes across the 2. Okay? And that is it. And we cannot draw lone pairs on the oxygens in this structure because where would we put 2 and where would we put 3? Right? Like, would it be 2 on this one, 2 lone pairs, and this one has 3? Like, we can't. So we just, when we're drawing that kind of structure, we leave it off. And that's why when we're drawing Lewis structures, in order to correctly show the number of electrons, we show the resonance structures as going back and forth, even though it's really a mixture of the 2. Is okay-ish? Okay, we're really going to learn about that more on Friday, but for now, you've had a little introduction to resonance structures. You now know how to do polyatomic ions. On page 27, sadly, there are 2 number 7s. I don't know what's wrong with me, but you're going to do number 1, 4, 7, 7, 10. Okay? That is your homework for today, 1, 4, 7, 7, 10. And you are also going to study for your test for homework. And then I have also given you tomorrow's homework. You know why? If I tell you before your test, will you listen to me? No. If I tell you during your test, will you listen to me? No. When you're finished your test, will you be able to absorb any new information? No. So I'm telling you today that tomorrow's homework, and it's already posted today, is page 25, number 1 to 8. Okay? That's some multiple bonds and multiple central atoms. Okay?
That is so true. After the test, I'm going to be like, what happened?
After the test, you're like, what just happened?
Like, what? I think it's not fun though. It's not fun. I think Jane, you're fun. You've been coming like every single morning. She's been coming every single morning. What did we get to? Okay, I came for like 2 mornings. 2 days less. Nobody's gonna be around on Friday, right? Us too. So we don't even know. If you're gonna be around on Friday, you can just work now. Wait. And you're also Christmas work. There we go. Oh, okay. Let's all remember tomorrow, right? Right. It says there's a quiz on it on the first day back. There will not be. Right. Wait, we're actually no, look. Yeah, Thanksgiving. Miss Spence, yeah. Staff know about like the oxidation and stuff on the
No.
I told you. Nothing on 10.3 except for like the trend. You have to know the trend. Okay, so after said it's just like that's what happens. Ma'am said nothing on that. But you have to know that why that's happening. You know why? On the other book, everything's on it. How First day back is so bad. Wait, this is the word. Do we just like do this on our own?
You just do it on your own at home. Yeah. Complete it. Show me when you get back.
Okay, so we just kind of like read it.
You read it. You do it. I made sure it was stuff that was like easy to follow. Do you know what I mean? Here's a formula. Throw in a few numbers. Right? It's all the stuff that you could easily learn on your own about gases. Yeah. Your earrings are so pretty. And they're like little snowflakes.
Yeah, they
oh,
are.
so good.
Because student council, it's mandatory to do Spirit Week.
And you're like, yay, here I am, Spirit. Look at me.
Friend.
I was supposed to dress like candy cane colors today.
Really?
Staff were supposed to dress candy cane colors. I think.
Mr. Colbert went all out.
Did he?
Yeah, he did.
Nice.
Because my friend, she's a spirit coordinator.
Oh, yeah.
She always gets mad at me if I don't do it.
Ah.
I was like, I did it.
I was like, okay, I can try today. I have white. Yeah. And then I have red.
I mean, it's not that hard to do. So.
No. But it was supposed to be white and red, and I'm like, I could do red or I can do white because I have a red shirt and I have a white shirt.
Red, though, so.
I have a red shirt, I have a white shirt. I don't have like red and white, and I don't have like a white sweater that will go over any of my red stuff because I got one, but it's like a little summer one. It's not. It's only meant to go over like to give you sleeves, right?
Yeah.
No.
I'm here tomorrow. You know what I'm doing?
Is it pajama day tomorrow?
Yes.
Do I get to wear my pajamas tomorrow?
Wait, guys, guess what Taylor's has PJ on?
So exciting.
Wait, look. No, I forget every single time I always wear sweatpants and a hoodie. I have to be as comfortable as possible to take a class. I usually need to know and that that's kind of like my good luck. Yeah, my focusing. Yeah. Like I look like a homeless person. Jeez. I'm thinking of just wearing like my PJs. Yeah. Watch me look homeless.
Yes.
So watch me look homeless. Watch me crack. It's actually more funny.
Let's see.
I said it.
Because AP tends to be like,
Did you just steal my periodic table? Bro. Thank you so much.
22 multiple choice. You're gonna like this one.
Oh, I did something else. Wait, is this the same thing as this? Yeah, right? Because this is also for homework. Oh, that's tomorrow. Oh, my bad.
16 marks written response.
Wait, so how many?
22 multiple choice, 16 written response marks.
Marks. So
Marks, not questions.
how many questions?
22 multiple choice. And then for the written response, there's 16 marks.
There's just one question.
Yes, just one gigantic question. No, I don't know how many questions there are, like 4, 5, 6, somewhere in that neighborhood.
Oh,
You know?
one gigantic.
No,
question.
not one gigantic question. No. That's what AP likes to do, though. They like to have a big question out of 10. But you'll usually find that most of them aren't that much related to each other, other than they're using the same chemical.
Can you stop stealing my food? Wait, I need to see yours. I have a great explanation. What? And this is all you do. Bro, that's so real. Stop. That's so. I'm so lucky as
A little bit.
Bro, I actually can't. Okay, no, because I've been transferred to another university. You're like my you don't need to know. I'm not watching my wait, but isn't I
I don't even.
oh, is it CL?
No, like, he is a.
Is it CL, right?
Oh my Jesus. No. Girls' bathroom is okay. Boys' bathroom, throw joint. You think you're going to that? And then he'll describe the war zone that is the boys' bathroom.
Damn, it's all. No, it's actually disgusting. No, you know what? Yeah, and there's a bunch of creating rubber stalls. Like, I just want one stall to do
Okay, you know what? You are older, you say get out. In that voice.
I don't know what both of them mean.
No, but seriously, do it. Come get me. I will go in there and I'll be like, get out.
No, I actually need it. Yeah.
Go back to your class stopping.
That's so
Anytime you need. I would be happy to do it. It would bring me joy. It would. Sometimes I like yelling at people who are doing things wrong that make life harder for other people.
I keep my business the bathroom like
There was someone parked
the
in the
most I
spot
ever
today.
did
Like,
I don't know.
they're parked like this.
Because first of all, in every station, I should have how much you want to bet it's
So I parked here because I'm small. So there's now like this much room in my car. An old car. So I'm like, you know what? You're going to have to get over here.
Oh yeah.
And I'm like, I don't care. And if they bought my car, there's no car. It's seen better days where I've gone long gone over.
How much you want to bet?
Yeah, why not know like that?
Oh, you have to. It just made
Oh, this is where you're going.
I want to see this. I want it. Okay, I see. This is not. Exactly. No, bro, you might
Did you just say no? This is alright. There's right the electron configuration. Well, don't you write the electron configuration?
Yeah, that's not calculated.
Yeah.
So there's only these. Three calculations.
And then ionization. Plugging in the numbers.
Bro, what is this?
Do you software anything?
You have to, no, you just write the equation, but you have to write it like you have to put the correct part on it.
Yes. Really? Not
For these, you're making my iPad lag.
Wait. Just three graduates.
Yeah, like here, like first,
Not yet.
like first, second, third, fourth.
Three graduates just came by and they're all like, "Oh, thank God we took AP because we know how to work hard." So they learned how to work, and it's applying to. I got two of them were in business at BCIT. What was it? Finances at BCIT? Yeah, finances at BCIT. Huge workload, but they're ready for it because they've done AP courses. And one of them is doing actuarial science up at SFU.
What science?
Actuarial science. It's like insurance calculations and stuff.
Oh,
I think you make big money doing it.
I'm not usually a lot of things.
but isn't that math?
Yeah.
Yeah.
So you got to be good at math.
I'm not.
A, I'm not good at math, and B, I don't find it that interesting. So even if I were good, I would
Hey,
No, I didn't. I'm sorry, I didn't finish. My brain like
first,
that's a board thing.
like
Depends
depends
on
on
how. And I was like, what
and then you have to see like the stars.
Whoa.
You have to understand her signature like 100%. Girl, I got it, girl.
No, this is the trend.
Okay,
This is it's just you don't know. I memorize it. I remember that these two are safe. These two like change.
I remember getting rid of the
Wait, why did I do that? It's first on the chart, right? Like X is -1. Oh, right. Oh, we look at that. And then if this is +1, like minus this is.
Yes.
Okay. So photons use.
Okay,
Photons use to
because
take out an electron,
if you,
right?
let's say we have Jupiter and Earth, okay? So like if, or actually let's do the moon and Earth, okay? So if you're on the moon, you're gonna like drop like this. And you're less stable, you'll sort of like bump around a little bit, right? If you're on Earth, and you're like, and you can't, like I'm not kind of like if I move a little bit, it's not like I'm floating up. You know, if I do this, I'm not like
Sounds about right.
wiggling around and stuff. So I'm more stable because I'm close, because I have more, there's more mass. The Earth has more mass, which gives it a greater force, which means I'm at a lower potential energy than if I were near the moon. It's keeping me more secure. So if I were equidistant between the moon and the Earth, I would move towards the Earth because that is more stable. So it is because for William,
Wait, you have a right?
Yeah, just farther. Yeah, just farther away. So you can say less.
So I can say, like, I want to be less favorable.
Sounds like an all department.
Alright, so no.
No.
And if you want to, if you get tired of getting
Right, F2 bracket, FC, and then bracket FC. No.
You absolutely need everyone to add it, is that good? Yeah, actually. What else is this?
Oh.
Yeah.
No, it's held us tightly because.
Okay, so
Are they putting some?
I'll be like, yeah.
It was bumping myself.
This one? That is for valence electrons because it takes into consideration the nuclear charge and the charge of the core electrons. So it's the charge felt by the valence electrons. So if you're looking at the force on the 1s electrons, you're not looking at Zeph anymore, you're just looking at the nuclear charge. There's no shielding electrons in between the 1s. It would, like, it would just be Z. It would just be the inverter task.
You take into consideration the ones.
It'll be like
Really good, Ron.
No, some calculations. Yeah.
cation is smaller. What does rate mean?
Yeah.
Rate.
Radii.
Wait, there's two radians. So it's just saying like in general, like, I'm not pretty more is more energy. Yeah. That's the same thing. Okay, so the cation, small point. Because,
Oh, just there, I was on this one. There, yes, you're lower. Oh, no, that's true. And then they're gonna be. They go for another.
Maybe she was happy with you.
So. Yeah, go ahead and see if I can. Yeah, we can, one slot.
Wait, so this is, you're on.